One of the strongest forces on the internet is the belief that someone else is wrong or something else is wrong. That it's wrong, they're doing it wrong, and it needs to be put right immediately. And as we know, that's not always the most positive motivation on the internet. But it can be. It can be the thing that pushes us out of the status quo. The thing that forces us to make fundamental improvements rather than just incremental ones. That burning feeling that the current way we're doing things is wrong, it can drive genuine revolutions in programming. It can upset the apple cart. And it can also be the drive that pushes us programmers out from behind the keyboard into starting some genuinely new businesses. Some of the most successful businesses I know started with someone saying, the current way we're doing this software isn't good enough, and the only way I can change it is by stepping outside the current system. And that was kind of the starting point for today's guest, Joran Dirk Greef. He had an urge to build an open source database called TigerBeetle and then build a company around it. From looking at the current status quo and wanting to change things radically. And it's still early days for TigerBeetle. They are just about to go into production. So I'd say, they're reaching the end of Act 1 of their story. But I think that story, that journey from discontent to inspiration to launch, it's one that speaks to all of us programmers who have a little slice of entrepreneurship in us. And along that journey, along the way, Joran has some really interesting ideas about how we should be doing systems design, clustering, network communication, reliability, integration testing, all these things burning to build something genuinely new, which is putting Joran in a heck of a road, a long road. And yeah, we're going to meet him at a waypoint on that journey and hear the story so far. So I'm your host, Chris Jenkins. This is Developer Voices, and today's voice is Joran Dirk Greef. My guest today is Joran Dirk Greef. Joran, how you doing?
Hi, Chris. I'm doing really well. Great to be here.
Good. And where are you coming from? You're coming from somewhere in South Africa, is that right?
Yes. Interesting thing is, we are actually same time zone, London time, best time zone in the world. Most overlap with all the continents, but I'm calling in from Cape Town.
So nice. Yeah, it's on my list of places to visit.
Okay, you haven't been yet.
Not yet. I'll find an excuse soon.
Okay. Well, you've got a developer friend here, so I will tour you around.
I'll look you up when I come over.
Yeah.
See, now the reason I've got you on, your story starts very much in Cape Town and a project around there, right? And one thing I'm always interested in is developers who have such an itch to scratch that they end up walking along that road saying this should be a real product and a real business. So let's start with where you got the inkling of that. You're working on some project for payments. Fill me in.
Yes. So I love that question. I can relate to that. I think this was like I think it was a 16-year itch in the making. And then COVID happened, and COVID was a catalyst for a lot of people, I think, to do a lot of interesting projects. It was not an easy time, but I studied. I was always into coding as a boy, and I loved coding, and I always wanted to do a business, and so I actually studied accounting at university because I understood. People told me, that it was actually on my list of things not to study. I had a list, 10 things never to study, and number one was accounting.
You literally wrote down a list.
I think so. I had it in my head at least, and so accounting was top of the list. And yet, I always wanted to do a business, a startup. That was in my blood, in my nature. My grandfather immigrated from Netherlands, and he built his own business, and my father built his own business. And so it was just a thing that I was always going to be an entrepreneur, or just someone to start a little company, And So so I had this conflict. I didn't want to study accounting, and I wanted to start a business. And people actually spoke to me and said, well, look, accounting is a great way to see the world of business because that's how you describe business is accounting. And so I thought,
Yeah.
oh, okay. So I went and studied accounting instead of computer science. And then I actually got back into coding, thankfully, and I got into startups. But it was a long time, like 16 years or so, of just honing my skill and practicing and coding and coding and coding. And that was a period where I could learn a lot and discover a lot of techniques and get into storage systems and how to write fast software, how to write safe software, and learn. And it was incredible. Daniel Lenoir, the music producer, used to say that he spent 16 years in a cave learning how to work with sound engineering equipment, and I kind of can relate to that because I was in this cave in Cape Town, in somewhere inside Table Mountain, just for a decade or more, just practicing. And then
learning
then
your
all of
craft.
us. Yeah, and then COVID happened, and the next thing I knew, I bumped into Adrian Hope Bailey on a soccer field, and he said, "Well, he's working on this payment switch," and I had no clue what a payment switch was. But he brought me in to consult on it and to see, how can we make this payment switch faster. And that's sort of, that's fast forward. That was now 2020, and so what was interesting there was that I had this background of doing things differently, living in a cave in Table Mountain, honing my skill. And so I had specialized in the Galapagos Islands, and become this interesting database developer creature.
You've evolved to a slightly different genetic path than everyone else.
Yes, exactly. And then what happened was I came up to this payment switch, and we had to see how can we increase the number of transactions per second. If you gave it a lot of high-end cloud hardware, you could get 2,000 transactions a second, which is a lot. But that wasn't good enough for me. I thought, well, can't we do 200,000 a second? Can't we do 1 million? Why not? Because I understood from some of the experiments I was doing that even a spinning disk is really fast. It can write sequentially 500 megabytes a second. And that's not even solid state, So Flash can do. You get devices already that are beyond 3 gigabytes a second. And if you think of the information, you think of the raw materials. You have disk, you have network, you have memory, and you have CPU. You've got these 4 physical raw materials, and you can reorder them in an interesting combination. And why can't you process transactions really quickly? We've got these incredible raw materials. So I looked at the switch, and from the very first second of the engagement, I was already drawing on the boardroom table. Here's another sketch for something totally different that could power the switch, kind of like Iron Man. Take out the old heart and put a new one in, and suddenly you've got more. You got all this, this energy.
Are you allowed to tell us roughly what the existing architecture was for comparison?
Yeah, so sure. Thanks. Great question. So I think this would be helpful, for people listening in. So the existing architecture was a MySQL database. SQL rules the world. So you had a SQL database. You had 10,000 lines of application code around the database, like we all do. And obviously there was a lot of Kafka streaming everywhere. And that's still there. That's kind of orthogonal. So the heart of this payment switch was a SQL database that was tracking transactions, basically bank balances and transfers between bank accounts for the participant banks using this payment switch. So you can think of it as like 8 rows in a SQL table, 8 banks, 8 rows, and then you're doing a lot of transactions across these rows. So it's actually so simple, really simple. You've got a table of accounts, and there's 8 accounts, and then you've got a table of transactions, and transactions, that table is big. That's the whole financial history. But the interesting stuff is that you're really just trying to you're moving numbers, you're doing addition and subtraction across 8 rows. And to do that, there was 10,000 lines of application code. Yeah.
It seems, okay, this is always one of those things where where until you actually see the code, you don't realize the complexity you're not seeing. But on the surface of it, that seems like disappointing performance, given that you're only swapping money between 8 different accounts. Yeah.
Yes. And I think this is the interesting thing. What I learned is that I think, just in general, as you work with a SQL database, we denormalize our data or whatever. We've got different, then sometimes you have, you've got indexes and you've got tables and you've got schemas and design. But how often do we stop to think how many rows are going to be in this table? Are there going to be 8 rows or 800,000 or 8 million or 8 billion? And what's very interesting with this actual domain is that very often you actually only have like 8 banks, and say we've got 8 rows, or you in practice you actually have a little bit more. So I am simplifying. Maybe you've got 16 or you got 32. It's some multiple of the number of banks. But very often you only have 4 banks or 8 banks or 16. It's pretty much the same order of magnitude. So the table is actually very simple in that sense. You can see it. This is like an Excel sheet that could fit on a screen without horizontal or vertical scrolling. And
and probably did actually, in the prototype.
Yes, exactly. But the performance then of 2,000 transactions a second is actually not bad for a SQL database. And that was the other thing I learned, is that if you do one network round trip to do a transaction, you can only physically do so many, according to your network bandwidth and according to the write locks that are going on in the database. And remember, like, the database also has to write to disk for that transaction, and it has to call fsync. And there's only so many fsyncs that a disk can do a second. And obviously now with Flash, that's gone way up. But when you put all this together, row locks, individual row locks, and network requests, and round trips, and latencies, and disk latency, there's always a fixed cost that you pay to write even the smallest of unit of information to disk durably. You're going to pay a minimum fixed cost. And then as you write more, you're going to pay more. But you've always got this minimum threshold whenever you want to get something to disk. But then if you think about it, we typically use SQL databases, and we do one SQL transaction for one real world event. So one real world event is one physical SQL transaction. In other words, one logical transaction, one financial transaction is one physical SQL transaction.
And that has a minimum cost, right?
And that has a minimum cost, exactly. And so kind of the 2,000 is not bad, because Simon Iskildsen has got a fascinating blog called Napkin Math, and he dives into this, one of his posts, how many fsyncs can MySQL do, if a MySQL could do fsyncs, or Postgres. And that's a really interesting question, because it brings in things of group commit. Obviously, the database is going to internally batch some of these transactions, so to try and amortize that minimum cost. But kind of when you look at it, like hand wave, the rough napkin order of magnitude is maybe you can do 10,000 transactions a second. That's like your theoretical limit for these designs. Yeah.
Okay, so now having convinced me that that's pushing on to the limit, what makes you think you can do better? What makes you think you can get up to like 500,000 or whatever numbers you're aiming for?
Yes. So this comes back to scratching the itch for a long time. And what was funny was the very first day of the engagement, we were sketching our tables in the office. I was thinking about this morning, but there are these white tables and you can draw on them. with a permanent marker, and then you've got like a little, you can rub it out. But you can actually, all the tables in the office, you are supposed to draw on them. So they encourage graffiti. So, and I mean, if it wasn't for that, maybe TigerBeetle wouldn't exist, because, we were in the boardroom where I am now. We were at the conference for this payment switch. We were looking at the architecture, and already I was just drawing on the table, and it was my first day in the office, and I didn't feel bad drawing on the table, but I already was sketching out something that I thought could do much better. And to answer your question, it all comes back to just taking a step back and saying, well, look, we've got incredible raw materials at our disposal. You've got NVMe that can now do 3 gigabytes a second of sequential write. We have like raw information, like there's a minimum size in bytes to capture the information content that's being processed by the system, by this raw materials. But what if we could, reorder the composition of these raw materials in a more optimal way? And basically what you have to do is you have information that flows into the switch network. Network bandwidth isn't really a problem. It can handle quite a lot of information. Then you have to write this information to disk, and that has a minimum cost. So there's an advantage that you maybe write 1 megabyte a second. 1 megabyte per, not 1 megabyte a second, but 1 megabyte for each syscall. Because that's, you don't want to write 1 byte at a time, or 100 bytes or 1,000 bytes. You want to do something a little bit bigger, because that just amortizes that syscall cost. And if you start to do that, well, you can see, then after that, you've written it to disk durably. Then you have to run it through your in-memory state, and you can picture your in-memory state as just a few hash tables. So again, you've got 8 hash tables. You've got one hash table with 8 keys in it, and each value is the bank account balance for these 8 banks. Again, I'm simplifying, but this is really the skeleton, the bone structure of this human that we're trying to create. You can start to see the form if you can understand this, that you've got one hash table in memory, you've got 8 keys, 8 balances, and well, how fast can you write to a hash table? And actually you can do, this was some of the work that I had done, experiments, you can do some of the new high performance hash tables can do at least say 10 million inserts a second, which makes sense because the memory bandwidth is pretty good, and you can look at how many nanoseconds does it take to do a cache miss to go to a location in memory, and it's maybe 70 nanoseconds or better, and you work that all back, and if you know that there's also memory parallelism. The chip can access 10 cache lines and pull them from main memory in parallel. You start to see, what a hash table can do. And now, you've got network, then you write to disk durably, then you do a lot of hash table operations, and then you're done, and you send an ACK back across the network. And that's kind of
you're doing this event sourcing trick where you capture the raw data, store that durably, and then do the onward processing. And then you don't have to worry about the onward processing being quite as durable because you can always reconstruct it.
That's right. And that's kind of using a log. So event sourcing, or thinking of a database as a log. There's that classic saying, the database is the log, and everything else is just a cache. And I had a chat, with Alex Gajago of Red Panda, and I asked him, because I see Red Panda as a database, which is a funny thing. People will say, "Well,
it's
is
one
it
of my
really?"
favorite debates. Yeah.
Yes. So I asked Alex. I said, there's some of our friends will say, "Well, is it really a database?" And obviously, I think it is. And Alex,
I'm gradually coming to the conclusion that if if you tell someone who's used to databases that it's a database, they'll be disappointed. But if you tell someone that's used to logs that it's a database, they'll think, yeah, this has way more power than I thought originally. But sorry, you had a quote.
Yes.
I interrupted you. You had a quote.
No, well, that's that quote. The database is the log, and everything else is a cache. But that is actually how Postgres works. MySQL, all these systems, they have write-ahead logs. They have a log.
Yeah, and that's really the master record that you don't get to see.
Yes, they put it in the log. Then there's some processing. There's going to be more data written to disk, as indexes are updated. But really, that is all. You can think of that as cache. Because if you, and this is also how the databases guarantee atomicity, so crash consistency through a crash, or what they call crash consistency through power loss. So the database is busy doing things, updating indexes, doing a lot of work, and then you pull the cord, and really it comes back to the log. At startup, it's going to go back to the last known location in the log, and it's going to redo that work. There's many ways, obviously, of specializing on this, but this is the big idea: is that you've got network, and you've got a log, and then you've got in-memory work, and maybe you'll have more storage work later. So I kind of did see this through the same lens, and this is even how file systems work. For example, ZFS also has the log, and then there's copy on write. But taking a step back, I thought, well, the information content of a financial transaction, it's, this is another question. What is a transaction in the OLTP world? It's kind of like you've got the who, what, the when, where, and the why. So that is OLTP. Who, what, when, where, why, how much, and you need to do a lot of that, and you want to be highly available and online. And I think that is OLTP. Who, what, when, where, why, how much, and basically, if you squint and look at this, which I did as an accountant, I said, hey, OLTP is really double entry accounting. Like, it's the same thing, because double entry accounting, we use this. It's been the schema for hundreds of years to model businesses, any kind of business that wants to track business events. They want to track the who, what, when, where, why, how much. So it's the
original event sourcing, right?
Exactly. Original event sourcing. It has all these properties that are very friendly for our raw materials of compute and storage and network. And you Alice, Bob, that's the who. What? Well, it was Alice reimbursed Bob. And there's the why. It's the reimbursement. The how much is the amount. The when did the transaction happen? Maybe there's another when as well. When was it recorded, and when did it really happen? There's a where as well, like you want to track jurisdiction. And I was thinking about this yesterday. As a developer, like, it took me a long time to realize, yes, UTC timestamps. Just use UTC timestamps. And then it took me even longer to realize, no, UTC timestamps are not enough. You want to track the where as well. Like, you want to track the identifier of the locale, so that you can, DST, or, the classic calendar app. You want to show someone a time that makes sense in their time zone.
UTC is data, and everything else is formatting. That's my opinion.
Exactly. Yes. And if you know the when and you know the where, you can do the formatting. And But double entry actually actually captures all of these quantities for you. It's a transaction between two people or places. Something moving from somewhere to somewhere else, like Google Maps. Get me a direction in Google Maps. That's double entry accounting. I want to go from Cape Town to London. How long is it going to take? It's place to place, or person to person. It's OLTP. I'm obviously being very hand wavy here, but I really think, in principle, like, the heart of OLTP is tracking these things, these business events, and double entry is a great schema for that.
I got my career start with software systems for double entry accounting. And I still think it's one of the great data models and the great understanding of how you model what's actually happening in the world. Yes. We should get back to your journey, because you've got all this double entry accounting knowledge from your accounting training, and you've got an architecture you think is going to work written on a desk, which is the first time I've heard that as a design tool.
And it got rubbed out, Chris. It got rubbed out.
That's why the back of a napkin is more durable.
Yes.
But how did you get onto the point of actually cutting this into software and seeing if it worked?
So, yeah, I think that's the great tension, because you have to always build trust. If you're a consultant on a project, you can't jump in and say, well, we're going to, redesign Postgres or MySQL in terms of the optimal configuration of raw materials from first principles. Yeah. And so we actually, this was the best part, I think, is that we actually looked at the switch and we said, well, the heart of the switch is OLTP, it's SQL transactions. There's thousands or tens of thousands of lines of code. We could read this, or we could see, where do we talk to the database? And let's instrument that. Let's trace every single SQL query that flows through the system. And let's send a lot of payments through, a lot of financial transactions, a lot of OLTP. Let's see the physical transactions that are being issued across the network. So we traced the SQL. And then what we saw was, for one logical transaction, there would be, say, 10 to 20 physical SQL transactions. And you could optimize that further. Some systems do one SQL query for one physical transaction, for one logical transaction. You can do that. This particular switch, there were good reasons for being between 10 to 20. But this was interesting because you start to see there's an impedance mismatch, because we're really trying to do OLTP. We're trying to do transactions processing, real world business transactions, business events, using physical database transactions. But the original, as far as I understand, the original meaning of OLTP was always in the sense of, what does the user need, first, and then do you have physical transactions to do that? Physical transactions to implement, because they are real world transactions. But you see there's an impedance mismatch. For every payment, there were like 10 to 20 network requests, fsyncs, etc.
Yeah, there's a clear disconnect between the logical world and the reality of how the software is modeling it. Yes,
exactly. Yeah. And in the past, this didn't matter because disks were so slow. It really didn't matter.
And transaction volumes were never nearly that high, right? No one expected. Yeah.
Exactly. So I think, this is my thinking lately. I think for a long time, OLTP was very welcoming. It said, yes, and we're also general purpose. You can put all your metadata, everything in the same database, and we're OLTP, but also general purpose database.
Bless you.
Thanks. And that was fine for a long time. And then I think there's like a divergence, OLTP and general purpose, because of this impedance mismatch. So coming back to your question, when did we decide, to do something different? I think I'm really grateful that we didn't immediately. We first analyzed the switch and we could get these insights, really understand the problem first, rather than try and, come up with a solution in search of a problem. We could really understand the problem deeply and see, yes, actually there's only on the order of 8, 16, or 32 rows in this table, and there's a highly contentious workload. So straight away you start to see, it actually doesn't make sense to horizontally shard, because there are, there's contention, double entry. You're going to update one bank account and update another one. You almost, and sometimes you want to update all the rows because you're doing very interesting financial contracts where they literally touch all the balances. So sharding isn't going to solve the problem counterintuitively. Now it's going to make the CPU wait even more, as you start doing network requests. And so I think that we did this work for like 6 months or so, or 3 months in. At 3 months in, actually, then there was just this period where I think 16 years had built up. And it was actually a Sunday afternoon. It was raining. My one co-founder, he does his best work when it rains, and I think I do mine when the sun shines. But this happened. It happened to be raining. I had the fire going. I was listening to Black Keys, this album El Camino, which is great. And it was a Sunday and COVID, and I banged the keys for 5 hours, and I sketched these raw materials, and you got this prototype that could do like 200 or 4. It could do 200,000 two-phase transfers. So, which is you're doing everything twice. So basically, it could do 400,000 financial transactions a second. And this was just a rough performance sketch, like back of the envelope, and it was JavaScript. So but it had all the ingredients. It had fsync there. It had cryptographic checksumming even.
Oh, really?
Which, just to really
so
see
more than just a very simple prototype.
Yes. Yeah. And it was trying to see, if we sketch out the network protocol, the disk protocol, the in-memory hash table operations, the real thing that could actually work, and it could work. So it was very basic, but after 5 hours and maybe a few days more work, we actually did plug it back in. We did a heart transplant. We took the ledger database out, this MySQL and application code. We took that out. We put what we called ProtoBeetle. We put ProtoBeetle into the switch. And it took a day because the design had come out of the switch, so we could put it back in, it extracted from a real problem. And straight away, the switch that when we evaluated it, we had this trick where we would try and evaluate it on really small hardware. So it's very easy to do benchmarks where you have the best hardware. What we would try and do was have minimum viable deployment. Like, what's the smallest, GCP instance we can deploy this on, and the minimum number of instances. So we used to benchmark like that. And in those configurations, we would only get 76 transactions a second. And when we put ProtoBeetle in, we could get to 2,000 without, fixing any of the other performance issues. So ProtoBeetle itself, if you use it properly, you could get 400,000 a second. There was a lot of other overhead in the switch, but it already made a order of magnitude difference.
Was that with the same level of guarantees about transactional safety, durability, or are you cutting corners on that?
So ProtoBeetle was just a sketch, so it definitely wasn't beta ready, and but it did do cryptographic checksumming. It did do logging to disk. We were basically trying to evaluate the performance if this could work. So it wasn't a plane that you would sell tickets for, but it was like a plane that you could launch off a cliff and see that it flies. And whether it lands is another story. It didn't have landing gear, didn't have parachutes, or.
Okay, we best go on to the what happened next after that prototype.
Yeah,
because I'm hoping you've built a plane that we can actually fly in at some point on this.
I think that's the whole question. That's the heart of it. It's like you can say to people, "Hey, we've built this plane, and it's so much faster." And they're going to ask you, well, is it as safe, as our regulated planes? Is it going to land me safely? And you'd be like, no, it's just really, really fast. So, and then you realize like how much work goes into safety. How do you make a plane really safe?
Yeah, and how much speed do you sacrifice on that road?
Yes, exactly. But being involved with the payment switch again was a fantastic opportunity to learn, because you realize that actually it's not good enough to say we're going to be as safe as all the regulations and the standards and the existing planes, because people are still going to say, well, you say you're as safe, but you're still a startup. It doesn't connect with people on a human level to say that you've built a new database and it's as safe as something that's 30 years tried and tested. People are going to be, well, that's table stakes. and I'm still going to err on the side of 30 years. I know you're as safe, but you're not 30 years.
You've got an uphill battle on trust if you want to turn that into a business. Definitely.
Exactly. So it comes back to trust. And so then we realized, well, there were a few factors in this decision that actually these systems were 30 years old. You spin the coin around one more time and you carry on with that and you go, well, actually they're 30 years old, and there's been tons of storage research. These were those experiments again in the cave, and like places like UW-Madison and the FAST conference, incredible research every year testing these systems. And that's kind of the other side of the coin. They are tried and tested, which means in the research, they know how they fail. They've all the latent correctness bugs, how you can lose data through fsync gate, a lot of consensus systems that the design of the write-ahead log is actually not fundamentally safe, and you can have global cluster data loss with a raft, with a lot of raft clusters. Some of them are patched for this, but the stock standard raft consensus doesn't get you there safely. So there was a lot of research around safety, storage fault research, distributed systems research, which was also at UW-Madison. And then we started to see, okay, yes, we are going to build a database, and it's the perfect time to build it 10 times safer. So again, like orders of magnitude, it was so much fun. You realize, hang on, like that moment of tension, like, yes, we're just going to do this prototype. You get past that, and then you realize, well, now we can do this 1,000 times faster and 10 times safer. And 10 times cheaper, because actually we made it 10,000 times faster, but let's give 10x of that for cheaper, small hardware, rusty hardware instead of, state of the art. So how can we make something that's really fast and small and much safer? Because that moves the needle, and then that's really what you want, is far more safety. So happy to drill into more of this, Yeah.
So let's get concrete about the implementation of this, because I know you've got your design idea there. The prototype has proved, and you've decided to go ahead. You've made some interesting choices, I know, about how you're going to implement this. And the first, most obvious one that jumps out at me is your choice of programming language.
Yes.
You didn't stick with JavaScript as in the prototype.
Yes, I didn't stick with the memory safe language. So I think probably the most surprising thing for someone, if they ask why Zig.
Zig is the language you've chosen. Yeah.
Yes, Zig is the language. Why not C? Why not Rust? Why not JavaScript? Why not Go? And I think the most surprising part of the answer is just to say, well, I truly believed then and now that Zig was actually the safest choice. If you look not only at memory safety, but safety of the system. So safety is a much bigger thing than only memory safety. Safety has to do with correctness. What makes for correct control flow? And I think what makes for correct control flow is simple, explicit control flow, a minimum of abstractions versus zero cost abstractions. So I would rather, I think more important than zero cost abstractions is to have a minimum of excellent abstractions, because that reduces the probability of leaky abstractions. So it's like subtle things like this.
We should probably just quickly step back. And for those that don't know the programming language Zig, give us the headline features.
Yes. Okay, great. So I was actually coming at this as a C developer. So around this time, I'd been doing most of my coding in C. And I was looking for a C replacement. I loved Rust. I had pointed like Ryan Dahl. I was just one of the people, and he had written Deno with the backend in Go, and I said, well, Rust would be great because then you don't have two GCs. So I did, but then I was a C developer at heart, and I loved the simplicity of C and the control of C and precision. But Zig came along and it just fixed everything that was wrong with C. But it also gave you far more safety. So it gave you checked arithmetic, which I thought was very important. And actually, if you look at a lot of newer languages, if you look really closely, most of them don't actually enable checked arithmetic by default in safe builds. So what checked arithmetic is if you're going to do integer operations on a type like a U64 or let's say a U32, and that integer arithmetic is going to overflow, in a lot of languages that's just undefined behavior, or it's a wraparound. And I had
and it was your fault
the
for choosing too small a U for the
exactly.
Yeah.
But many languages, you would be surprised. I think if everyone went home and double checks this, in a safe build, the default settings is checked arithmetic enabled. Usually the answer is no, which is very surprising, because actually you want checked arithmetic on where safety is mission critical. Because I had done a lot of security work in the cave, some R&D on how do you do static analysis to detect 0-day exploits, and it worked. You could catch them. It was really fascinating, but a lot of it came down to like, let's look at a zip file and let's see, is this zip file format, is there arithmetic overflow happening in these values? And if there is, chances are it's almost certainly a 0-day. It's going to attack the antivirus software that opens it up, because you're going to get arithmetic overflow, which will allow the malware to exploit something else. And you chain these things together and you get a CVE. So there's like checked arithmetic is really important if you look at things from a security perspective, I think. And security, you flip that around and, well, that's safety. It's a big ingredient. So why Zig? Well, it was one of the few languages that actually had it enabled in safe builds, and I thought, wow, that's a great design decision. I wish more languages had that. And then it had bounds checking, which is base. If you're in C, it's like walking blindfolded on the cliffs of Dover, and you're going to fall off so easily, and you really want bounds checking, and Zig gave you that. And you want, actually, like for distributed systems, the challenge isn't really memory safety bugs. There was a paper on this, I think on the order of like 90% of the major incidents in distributed systems are actually the lack of error handling around syscalls. And Zig was really great for that. Zig gave you first-class error handling, and the compiler would check, if you don't do proper error handling. You can't just ignore stuff. Even now, Zig has got a design decision that people have pushed back on, no unused variables. People say, well, I want to have my unused variables, but in terms of safety, like, do you really? Because often that's, in TigerBeetle, we've seen before Zig made this change, we could have had some, latent correctness bugs. We found them already, but this principle of not allowing unused variables is a good principle, from a safety perspective. Okay. So, and Zig is a very simple language, but fundamentally also, if you're a database, you need to handle memory allocation failure. You also want very fine-grained control of your allocators that you can use. You don't want to have just a global allocator somewhere hidden, and a panic. So again, C, it was either going to be C or Zig. And the way I motivated this internally was I said, well, we're going to do C. And then everybody panicked and they said, no, please, I want to be able to build this on my Windows computer. Like, please give me a proper tool chain, And Zig had such a phenomenal compiler. You can cross compile from Windows to Linux or to M1 chips. It was the first compiler to do that. And so it's just got a fantastic develop experience story. It's a great, lovely compiler. Like it's also one of the few languages that are also investing in the tool chain. The compiler is so important. So it was always going to be Zig, I guess, but threatening C helped.
That is a Captain Kirk level bluff there.
Well, I think it was unintentional, but retrospectively, let's claim it for Kirk.
Yeah, claim it as a win. Claim it as a win.
Yeah.
Okay, so we've got the architecture. You've gone for Zig. I know another thing you've wanted to do differently is the way you approach testing, which I thought was very interesting in the architecture. Take me through that.
Yes, thanks, Chris. So, yeah, and I guess just to add, both Zig and Rust, they're phenomenal new systems languages. So it was, again, like, are we going to invest in the last 30 years of C? Or, what, if we're going to write a lot of code, where do we want to be in 20 years' time? What language do we want to be using? And for sure, like Rust or Zig. So that kind of made it very easy. Testing, that was the other challenge, because building a database, it's a storage engine. If you're a single node database, you have to build a storage engine, and that's something like an LSM tree. Usually that's the big engine that powers these things these days. And typically, if you want to build this LSM tree and you want to get it production ready, they say, people say, like, it's about 5 years to not only to build it, to test it. Most of the time is dominated by testing. So you can build it in a year, but then you tune it in another year and you test it in another 3 years. And then, it gets widespread adoption, but that's 5 years. And the problem was, we needed a database that was not only single node like MySQL or Postgres, because we wanted a great operator experience that you just get automated failover and high availability. So you run TigerBeetle as a cluster of like 3 or 5 nodes. And we actually support some more interesting configurations, but this general idea, a cluster of 5 nodes, and your primary goes down and the cluster will automatically elect a new. It's basically backup and recovery, like automated for you, instead of you doing this, doing manual failover between in a multi-master setup, for Postgres. You don't want to do that manually at 2 a.m. Consensus can do that for you in a way that's automated and tested and highly available. The switchover happens within milliseconds.
Slightly aside, but did you roll your own consensus mechanism, or have you done something like Zookeeper?
Great question. So I think again, the answer is always safety. And I think it's surprising. Like, so we wrote, yes, we picked a new systems language. We wrote a new storage engine. We wrote a new consensus protocol. And the answer was surprisingly always safety, because again, the research was showing that the way existing consensus protocols were proven, that yes, they had formal proofs for Paxos and Raft, but the formal proofs missed something. They only considered how the network fails. They didn't look at how the storage fails. So if you want to build something that is correct for Paxos or Raft, you have to guarantee that the disk never fails. So each disk of the cluster may never fail, because otherwise the promise that was given during the voting phase of consensus, that promise could get revoked, which could undermine the quorums, which could cause the cluster to regress into split brain and global data loss. So these two protocols rely on perfect disk. They call it, in the consensus world, they call it stable storage. And the formal proof, there is no fault model. It just says disk is perfect. And that's fine. You can then solve that locally with logical RAID like ZFS. You can't solve it with most RAID, because most RAID, if there's a corruption on one of the disks, it's a guess as to are you going to recover in favor of parity or in favor of the corrupted version? It's just XOR happening across the stripe. So
Okay.
there's research on this too. RAID will make sure that your disks are in sync. But if there's corruption, there's not enough information at the block device level, checksumming, to know which is the corrupt version in the stripe and which is the real version. So ZFS can get this right. So you can run your consensus over ZFS, but now you're paying the cost of 3x or 5x global replication plus 3x local replication. So now it's extremely expensive. And again,
So what did you
ZFS. Do? Yeah, so these were kind of what motivated us. We thought, well, but the big problem too is that actually, like, these consensus protocols, if the storage engine takes 5 years to test, the consensus protocols take 10 years and they still haven't found all the bugs. And so, even if we take an off-the-shelf protocol, is it still safe? And do we understand it? Because we can take it, but then we have the responsibility to audit the code. We can't just bring in a dependency if we don't understand it. And understanding an existing implementation of consensus, that is, again, going to take 1 year or 2 years to build up that in-house knowledge. So what we thought was, well, sure, what we want is a storage fault model. We want to handle disk corruption, and we want to do that efficiently without local replication, because we already have the global replication. And there's been a ton, the last 10 years of research on LSM trees since RocksDB and LevelDB. So we didn't want to take those two because there's a lot you can do these days. For example, those have 1 second write stalls, which will bump your P100 latencies in your database. So short answer is basically we realized that there's this paper, UW-Madison, Protocol-Aware Recovery for Consensus-Based Storage. In other words, how do you build a distributed database in 2020? That's the paper. How do you build a distributed database in 2020? And the answer is that you really need to design your local storage engine to work with your consensus protocol and vice versa. So what that means is you want your storage engine LSM, if it yes, it must have checksums, but if it finds a checksum error, you don't want to do any local action immediately. You don't just want to truncate your write-ahead log, because that could actually lead to data loss in the consensus protocol context. So what you really want to do is your LSM and your write-ahead log of the database must be designed first class for your global consensus protocol, and vice versa. Then what you can do is, if you see a local corruption, you can actually ask the cluster and get a quorum correctly, and then you can say, well, what is the correct thing to do? Am I allowed to truncate this piece of data? And the cluster can say to you, yes, for sure, we know this was never committed, it's safe to truncate. And that way you actually keep the cluster going much longer, because now you can unstuck things. Yes, it's safe. You can quickly recover, truncate the log. For sure it's safe. But there are cases where you can't truncate the log because that log contains committed transactions, and you need to preserve your vote to the cluster. So then the cluster will say, well, no, you can't truncate. And really, you have to ask the cluster. You can't, most of the existing designs, they make this decision without reference to the consensus protocol, which is not correct. A long answer, we realized we have to actually, this is going to be one of the first implementations of how you do this. We're going to make an integrated stable storage that's integrated with consensus protocol, and the thing can be efficient. Use the global replication to recover local faults and do that correctly, high availability. Yeah.
That makes sense. We had an episode recently with Benjamin Bengfort about implementing your own consensus algorithm and how you could then have custom primitives inside the consensus algorithm. And it's exactly that, but this is a specific use case of that idea, which is really interesting.
Yes, yeah. No, I think that's often why this isn't adopted, because people will say, well, we're building a new storage engine for Raft, but we're not at liberty to improve Raft to be storage fault away, and so it's you're stuck. You've got the abstractions, but it stops you from getting to the system you really want. And but then
the desire to make consensus a black box is coming from the fact that it seems too scary to open that box. But you kind of do need to open that box if you want to get the right behavior.
Yes, yeah, and you do want to understand it. You do want to understand it, and it comes back to zero cost abstractions, because actually abstractions always carry a probability of being leaky if the abstraction boundaries are not exact, and this is a classic example where the abstraction of global consensus protocol in isolation from local storage faults is actually the formal proof needed to really consider the whole system, be a system proof.
One day we should have an episode with you and Benjamin for a Smackdown. That'd be interesting.
Oh, yeah, that would be great. I think I still haven't answered your question. How do you test
testing? We were talking about testing. Yes.
Yeah, I've just made everybody nervous. Like, they wrote their own storage engine, they wrote their own consensus protocol. Storage engine takes 5 years, consensus protocol takes 10 years, and we still haven't got all the bugs.
Well, I'm going to dip into that before we get to testing in that case, as you mention it, because some people are going to look at this and think all these safety properties are very important and great, but it sounds like you're disappearing down a rabbit hole. How are you actually going to get to production from that large work stack?
Yes. So I think the surprising thing is we found a silver bullet. I love Fred Brooks, no silver bullet, but we did find one in the cave. And this is really like credit to Foundation DB. They wrote Foundation DB very differently also. They wrote this whole database that you could run it in a simulator. So, what's the best way to become a pilot? And in the past, you used to jump in a plane and fly and crash. And then you survive and you get better and you put hours on. And then one day people realized, well, we don't want to keep crashing our planes. This is very expensive and we lose the pilots. So actually, let's build a flight simulator and we'll simulate everything, and you can crash inside the simulator where it's safe. So that's sort of what Foundation DB did. I think they were one of the first. Most databases are not designed like this. You have to fly them for real and crash them in production and get the issues. Foundation DB, you fly it in a simulator, and then the simulator speeds up time also. So if you have to run your database for 2 years before you hit the bug, the simulator can speed up the passing of time. So you can find the bug in 2 days of simulator time versus real, if you were to test a system with Jepsen, you have to run it for 2 years. Jepsen can't speed up time. So Foundations found this silver bullet, so valuable, it's actually called deterministic simulation testing. It's the idea that you design the database to be run in a simulator, because then you can speed up time. You can get to for example, so TigerBeetle, obviously, we did the same. We wrote our consensus and storage engine in a very specific way that it's deterministic. So given the same inputs and network latencies, the code will always execute exactly the same. And so you always get to the same answer, which means that now you can debug TigerBeetle, and from a single seed, you generate this whole SimCity world of events, and it's like a big bang, and a whole lot of chaos happens. But you can always recreate that. So if you find an interesting consensus bug, your team, you drop a little seed in Slack, and suddenly everybody around the world can reproduce this whole series of millions and millions of distributed systems events, and debug.
So this is like generative testing, but you're not just generating the fixed data set from that seed. You're also generating how reliable is my network model in this simulation? How reliable is my disk in this simulation? That kind of thing.
Exactly. And then what you do is you're simulating latencies. So
Yeah.
if and latencies alone are very interesting. If you simulate wild disk latencies, it could uncover a lot of interesting race conditions in your database code. And I'm sure, existing systems could do more of this, but you can do this in the simulator, wild latencies, network faults, and then storage faults. So TigerBeetle, some of the tests, we inject like 8% of corruption. Every time you read, the simulator will corrupt that read 8%. And that's something that I think almost no database can handle. There's a lot of checksumming, but usually the checksumming is there for crash consistency through power loss, but it isn't there to handle just corruption of everything in the data file. Like anything in the data file, let's just corrupt it 8% of the time on the read path, and then on the write path, we'll just 9% of the time we'll write to the wrong place. It will write anywhere.
So like shaking out that rare a bug.
Yes, and we just do that. We do that every day. It's very normal, so we operate like at extremely tight tolerances, like extremely rare bugs. And then the easy bugs become very easy,
Yeah. I almost hesitate to say this on record, but it seems like the military would be interested in running your database in the field if you've got that level of fault tolerance. Because I'm just thinking, where would you actually get 8% disk corruption when there's a battlefield happening around your disk, right?
Yes. Or if you boost your TigerBeetle into space and you've got all these cosmic rays. And
when I was a kid, TigerBeetle in space was my favorite cartoon, so that's perfect.
Is that really a cartoon?
No, I'm kidding. I wish.
Okay, well, maybe for the next generation of kids, we can make it happen.
You could have it as a little sideline merchandise. Okay, so we're sort of running out of time, but I do want to ask, what's your current status, like in terms of alpha beta production, and how are you going to get to production?
Yeah, so we're very close. We've actually only been a little over 3 years from zero, and already the consensus is tested to a tolerance that most systems couldn't survive, and the storage engine. So we're busy polishing and wrapping up and coming into some first releases this year. Starting a release process in September and tagged releases, and then we'll increase the guarantees of storage stability as we go. That's sort of the current focus now. Is let's just lock in our data file format. I guess the second leap we haven't really dived into, is at some point where can open source become a company, so, and that happened last year, November, this idea, TigerBeetle Incorporated. Yeah.
And what's your angle for that? How are you going to make the open source software pay for itself?
Yeah, so that was also kind of a tension. We were fully invested, and we still are always in Apache 2 open source, because we came out of an open source payment switch. So we saw how open source is crucial to a business. You couldn't have a business supplying an open source payment switch with software that isn't open source. Even the BSL wouldn't work because it's not open source. So it's the anti-business license. We couldn't have a business if it's not open source. The question is, well, how do you do a business then if it is open source? And that took me a long time to figure out. But I think the key is just that it's mission critical. So people want they want open source, but they also want people to run it for them, because it's mission critical. Or if they run it themselves, who are you going to call if something does go wrong? Because
so we may see TigerBeetle support contracts and TigerBeetle as a service before long.
Yes, yeah. I think, and it's quite. I would love that, and the more people running TigerBeetle, the better. Like it's kind of. I would never have worked. I actually joined Coil full time to work on TigerBeetle's open source, but I would never have worked on these things. I just see them as so valuable, a new distributed database I love ZFS so much, and I was always sad that Oracle didn't get the license right. And so I would never have worked on a new, distributed database technology if it wasn't open source, because I think these things are too valuable. They're bigger than a company. It's an ecosystem, so you really want this to be open source, and it actually makes business sense, to create an ecosystem around this. Yeah.
Well, I hope building the business around it works out so that you can keep the open source going for a long, long time.
Yes.
In the meantime,
thanks, Chris.
Joran, thanks very much for giving us the breakdown, and I'll talk to you again soon.
Yeah. Thanks so much for having me. It's been a real pleasure. So thanks again to you.
Cheers. Thank you, Joran. It's got to be said, he is biting off a lot there, but it's an interesting bite to take. And his ideas about testing, I think he might be onto something. He might actually accelerate the development of making that database reliable by a heck of a lot. So I'm going to put a link in the show notes to one of TigerBeetle's test cases. It's an easy read, it's well written, and it's interesting. The way they've modeled like cluster failure and disk failure, network failure straight into the test suite. It's probably the way we should be doing really, really mission-critical integration testing. Something to learn in that code. I think we're also, something to learn, going to need to have a dedicated episode on Zig, the language he's using. I'm keen to learn more about that, so I'll go and look for a guest. Stay tuned. And of course, the best way to stay tuned is to click subscribe and notify and all the buttons, whatever buttons your app has. If you've liked this episode, please do leave a like or a share or a rating or all three, because ultimately that translates into there being more episodes to come for a long, long time. And it makes my day too. And with that, I think I'll leave you to your day. I've been your host, Chris Jenkins. This has been Developer Voices with Joran Dirk Greef. Thanks for listening.